Welcome to another crash course electronics setup and programming video. This one will deal with ultrasonic sensors. So with the Elegoo robot, it already comes with one ultrasonic sensor, normally mounted up top here, and it's almost identical to the one that comes in the kit of parts. The only difference is that the connector here is a 4-pin connector, whereas the back of this one is a white connector that fits nicely with Elegoo's expansion board. So other than the initial wiring, and you can just use the DuPont wires on uh, the other kit of parts sensor, put all 4 pins in, and essentially it works the same way. So the first pin on your left, on the left of the video is a VCC, so that's power, 5 volts. Then you've got the trigger that emits the pulse, echo, which receives or outputs the distance essentially, and then the ground pin. So before we get to using these sensors, it's kind of good to know the basic principle behind it. So if we look at this over here, essentially, the ultrasonic sensor works just like a bat. So the idea is that you emit a pulse, and then if there's an object within range, and range of these sensors is usually somewhere around the 4-meter mark, 4 meter, 4.5 meters. Um, so if there is something in that distance, the receiver will hear the pulse, and with a bit of timing, taking into consideration the speed of sound, we can calculate how far it is. This formula is maybe not 100% correct over here, but essentially the idea is that the velocity of sound is 340 meters per second, or 0.034 meters per microsecond. This should say microsecond. And so you can calculate the time that it would take for the pulse to travel out and back in. There's a divided by 2 in here, and that is because the time should you don't really care about the distance it takes to get out and come back in. You just want to know what the distance is going to the object. So you have to divide that by 2 to compensate for the fact that you have sound going and coming back. Okay, so we'll actually cover the formula a bit more detail when we write the code. Um, it might be interesting for you to know that these two things are different on the sensor. So the one on the left, labeled T in the bottom right corner over here. So this one here is the transmitter, and this one here is the receiver. Some ultrasonic sensors have both in one unit. This particular one has it in 2 separate devices. All right, so let's go look at what the code would be for this. So let's go into Arduino app. Let's set up a new project in the project manager. Ultrasonic create. Let's go to the code and let us delete that. And we're going to start from scratch. All right, so first we want to define where our pins are, and we've already said that it takes 2 pins to get this to work, one to trigger the transmission of the signal and one to receive it. So we go to Sonic, so the trigger pin, and on the Elegoo, the built-in one, it's on A5 for the trigger. Let's just call that the echo, and that one's on A4. If you were to add the second ultrasonic sensor using the second one, you might want to use some of those other A pins. So A0 through A3 are free by default on the Elegoo car, so you could use those ones to add another sensor. All right, so um, let's actually look at how this works. If we go back to this page, there you go, and you look at the timing diagram. So what we want to do is we want to set our trigger pin high for at least, or for exactly, or as close to exactly as we can, 10 microseconds. So we want to set this thing high for 10 microseconds, and that tells the electronics, please emit the sound. And the sound in this case is 8 pulses that are spaced out essentially at 40 kilohertz. So it's probably about twice the frequency that humans can hear. Um, and then the echo pin, it's a little bit odd. it's not actually the sound coming back. It is a pulse whose width represents the amount of time that it took for this 40 kilohertz pulse to leave and come back to be heard. So if there is no object within range, you won't get an echo pin high. It'll just stay flat on low. And if you do get an object, this will be held high for as long as it took for the pulse to leave and come back. So that's kind of an important thing to know. So if we want to look at our code, let's start with just setting up the hardware. Okay, so we want to turn on our trusty serial port for debugging messages at 115,200 bits per second, because that's one of the commonly used ones that is reasonably fast. And we're going to print line ultrasonic test v1, just so we know we have the code that we're expecting to run in there. And then we're going to set some pin modes. So we're going to set the ultrasonic trigger pin to be an output. It's the signal we set for the sensor to receive. And then the ultrasonic echo pin, which to the Arduino is an input for that timing bit. And that's it for that. And then essentially what we're going to want to do in the loop is we're just going to want to get that distance and then print it to the screen. So that's all this program is going to do. So I'm going to write that we want a distance, fill in the blanks after. So let's say we have a function that we will call get distance in millimeters. I like suffixing the function name with the actual unit of measurement, because otherwise I find it confusing as to when I say get distance, am I getting that in inches and centimeters and meters and what? Um, I like millimeters because rarely do I need to divide down further than millimeters, and also given it's going to be kind of a maximum of 4,000 or 5,000 millimeters, it's not too huge a number to deal with the other way. Some people prefer centimeters, and that's fine, or if you prefer to do imperial units, you can do that too. The math will just be slightly different. So now we're going to say if the distance is exactly equal to -1, that's a special code we're going to return if we don't actually get a measurement back. So that's something we're choosing to use, or I'm choosing to use. So in that case, if I do get essentially an error code, I'm just going to print 4 dashes to say that this is not a valid measurement. Otherwise, I am expecting a valid measurement, and we'll call that serial print line, and we're going to print out the distance. All right, so my sensor should be getting called, and let's actually put a little bit of delay because we don't want that to fire infinitely fast. So we're going to say that if it's an error, 4 dashes, otherwise it's going to be the distance in millimeters, and that's what's going to be displayed on our terminal, on our serial monitor. So what is this get distance in millimeters? Let's just copy that because we're going to need to define that. It's returning an integer. So integers can be negative. Distances aren't usually negative. I don't think you're going to find anything behind you. So we're going to say get distance. It doesn't take any parameters. Let's void that, like that. Or in C++, you don't have to put the void. And we're going to have to now talk about how this is going to work. So I have already mentioned the first step is to hold this trigger pulse high for 10 microseconds. Now, most examples you'll find will actually hold it low for 2 microseconds just to make sure that the thing wasn't left high anywhere and that you actually have a low in order for the sensor to start a new trigger. So if you had forgotten to leave it high, if you had forgotten to pull it low, you want to do that now. I'm not 100% sure it's necessary, so that's something you could play with optimization. But let's grab the ultrasonic trigger pin and make sure that it is low for delay. Now we can't use this delay. This delay is in milliseconds, so in thousandths of a second. We want to be playing in millionths of a second, so we're going to have to call microseconds. Okay, so we want a delay of 2 microseconds. And then let's copy that, paste here. I'm going to hold it high. for our 10 microseconds. Oops, copy, don't paste. And then low again. Copy paste is a great way to code faster, but it's also a great way to introduce mistakes. Make sure you reread your lines after you've copy pasted. So right now what we've done is we've made sure this is low for at least 2 microseconds. Then we're going to hold it high for 10 microseconds, and then we're going to pull it low again. So that should satisfy this portion of the timing diagram. So us saying, please take a new measurement now, which will automatically trigger this event here. So we don't have to do anything about that. It'll just happen. So the next thing we have to do is start listening for the return pulse. So the way we do that is we're going to use this pulse in function. And let's actually, so we're looking at listening. So it's which pin are we listening on for a pulse? And what's the start of the pulse? So this function essentially times how long a pulse lasts. So we're saying, all right, echo pin, don't start this until it's low, and then wait until it goes high. When it does go high, start your timer. So it's like start a top stopwatch. And then when it goes low, come back from this function and return the time it was. So we're going to call this, it's actually a unsigned long because it could go on for a while. It's in microseconds. So we're going to call it echo time. Okay. So how long did it take to get the echo is echo time. And that's what this is. Okay. So if we look again at the graph, essentially it's going to make sure that the thing is low before we start, and then it's going to look for this high transition, the low to high transition. And once this happens, it starts your stopwatch, and then as soon as it goes low, it stops the stopwatch and returns the amount of time in microseconds that this lasted. That's what pulse in does. It is a built-in Arduino function. All right, so now that we have gotten the time, we need to check if it's valid, and the easiest way to do that is actually to use a timeout. So we want the ultrasonic timeout. Okay, we don't know what this is yet, but there's some value because I don't want to wait forever. If something happens and this goes high and it waits forever or never goes high, or I don't want to stay here waiting for this pulse to happen and stall my entire code forever until this may never come back. So this function optionally takes a timeout, which I highly recommend. And it also lets you, so if the echo time is exactly equal to 0. Sorry, I'm just put an if in there. If echo time is exactly equal to 0, then we've got an error situation. So this, if you look up the documentation for pulse in, and you can do that with any Arduino functions. If you do Arduino and the function, you'll find the arduino.cc website and the reference code, and you can find information on these functions. This is very useful, and you can see this one either takes pin and value or pin value and timeout. And there's example code and everything. And maybe more importantly, it says return, it'll be the length of pulse in microseconds. So it tells you it's microseconds in case you forget that. Or it's 0 if no pulse started before the timeout. Okay. And it also tells you the data type of the return. So like a smaller number might not be able to hold the return value. Okay, so since this says it's an error, and if you remember earlier, we said let's call -1 this error condition. So I'm just going to say return -1. And if there were other error conditions, we could return -2 for something else and -3 for something else, and then later on you could tell in your main program what kind of error happened in this function. We could have returned 0 for now, but minus or negative numbers are more often used as error terms. All right, so if it does succeed, so if echo time isn't an error, then we don't actually want to return echo time because we're actually not wanting a time, we're wanting a distance. So this is where the math comes in. So it's not echo time. What we do want to return is some kind of number. So if you remember the formula from earlier, what we want to do is echo time times the speed of sound, and I'm going to go in millimeters per microseconds. This is something we're going to define. So I'm going to figure out what the speed of sound is in millimeters per microsecond. So I don't want meters per second because I can't use seconds. I'd have to multiply this number, which we could. So if you have 1,000 microseconds, um, you have some point zero zero something of seconds. But to make things easier, we're just going to keep it in microseconds. And then I want millimeters because that's what I said my function would return. Okay. So we'll skip what that number is for now. And then we're going to divide by 2 because, as I said, we don't really care. Really what we're doing is we're taking the overall time divided by 2 times the speed of sound per in millimeters per microsecond. Sometimes putting this here is a little bit better for the compiler because it can essentially divide this constant by this constant before, like what during compile time. So then this will all be replaced by a number in your code. Um, that might be a little quicker to do the math, and you can even put this in bracket to force that math to happen first. And this never changes. That number will always be the same. So, all right. So now we need to define what this thing is. So let's copy that. Let's go define this, and we might as well grab this also because we haven't defined our timeout yet, which will give us a compiler. All right, so what is the distance? Well, if we take, let's write this as a comment, 343 is the typical dry air 20 degrees Celsius speed of sound in meters per second. And then if you've done physics, you know that if we're going to, let's say this is equal. If we're going to millimeters per second, because that's one thing we want to do, it's going to be 343 and add 3 zeros, millimeters per second, okay? But we actually want this in microseconds, so that means we now need to divide by a million, because there's a million microseconds in a second. So we're left with 0.343 millimeters per microsecond. Okay, so we're going to write that down over here as 0.343. And if you're not too sure about this, you can just take my word for it. The timeout's a little trickier because you essentially want the timeout to be longer than the amount of time it takes to go to emit the pulse, reach the farthest object, and then come back. So if we're looking at this one over here, if this object's at, let's say 4.5 meters, which seems some ultrasonic sensors are spec'd at 4, some at 4.5 meters. So let's say it's 4,500 millimeters. So that's that much on the way there and that much on the way back. So we're looking at 9,000 millimeters. How long is 9,000? How long does it take sound to travel 9,000 millimeters? That's the minimum value we want for our timeout. So we want that to actually be a little bit more than the time it takes to traverse 9,000 millimeters. So let's actually define our max distance. Just then if you change sensors or if you find that, oh, it actually has a slightly different distance, you can change it here and the math will work out. And then your timeout is actually going to be, so the max distance times 2 divided by the speed of sound we need first. Let's first bring that up a line or 2. There you go. Copy that. Like that. So essentially the inverse of the calculation we're using down here. So if you were to take the 2 and flip it on the other side and then divide by that, you're getting this formula. The only problem with this right now is that what if it is at 4.5 meters away? We might be getting really, really close to the edge there. So let's just add some room for error. So let's add 50 centimeters or 500 millimeters or half a meter of extra wait time. We'll be patient for a little bit longer. You may have noticed I have brackets on the far edges of this, and that's because when we include this into something, we want to make sure it doesn't mess up the math if you ended up putting this somewhere where the operator precedence would change. So if these were like all additions and you put that next to multiplication, it would actually multiply the last term. Just take my word for it. When you have defines, you want to do that. The alternative is to use the const int expressions instead of defines. Defines are maybe a little older way of doing it, but they're a little simpler visually, so that's why I'm using these ones. If you're using constant, you save yourself some of that trouble though. So if you are using defines and you have math or something more than one term essentially, make sure you put brackets around it. It'll save you some headaches. All right, so just a quick review. We set our pin low for a little bit, high for 10 microseconds, and then turn it low, and then we time how long the return pulse is, and then that time multiplied by the speed of sound divided by 2 because we're going out and coming back in will give us our distance in millimeters. And then the main program, we're just asking for it and we're checking for a return error code. So let's see if I've made any silly mistakes by compiling. Let's turn my robot on. That'll be a good idea too. And while it's compiling, let's just check that I have communication with my robot. Yes, I do. I don't have to log in, but TCP2 Elegoo works. All right, this is done. So now we're going to make sure to, so we have the right server, WWFIRST, we're Arduino Uno. I need to pick the right device down there. And now let's try writing to it. There we go. That's programmed. So now if we go to the monitor, the serial monitor, there we go, we're getting a distance. So let's go back to there. So I suspect it's catching the edge of my monitor, which is at 30, or maybe even the base of my monitor at 37 centimeters. Let's actually just take a cup, turn this over here, and see how that works. So now we're at 180, sounds approximately right. And if we move this in closer, it should be in okay, 7 centimeters, sounds about right. The minimum distance is somewhere around 2. Eventually the transmitter um, and the distance between the transmitter and the receiver is so close that you can't really measure anything closer. So it's about at 3 centimeters, which is pretty accurate. Eventually we'll lose this or start getting weird numbers when it's too close. So be careful about that. There you go. We just lost it a little bit. It's not really, there you go, if we put it properly. So you see we're getting a bit of junk. So you got to be careful with your code on this. Ultrasonic sensors are not the most reliable sensor. Point them in the corner and they go a little nuts too because that's some weird reflections. So you have to be um, wary of that. So when you're writing your code, it's probably a good idea to start measuring when you know something should be at a certain distance. So if you think something should be 50 centimeters away and it's reading 2 meters, you know you're not reading what you want to read. So yeah, so that's that. Also important to note, ultrasonic sensors are really slow. Like the amount of time it takes to traverse the 4 meters and back is in the 30 millisecond range. And so if you think your driver's station is reporting at 100 millisecond rate, so if you're doing a lot of measurements or you're expecting to get in a lot of measurements to do some really fast automated controls, you may be disappointed. The ultrasonic sensor might not be fast enough to read things. So also be careful about that. Don't be going at full speed towards an object and expecting your ultrasonic sensor to stop you when it hits 0. You may have to say, hey, I need to stop at 10 centimeters away in order to slow down fast enough to not hit something. So that's something you'll have to experiment with. But yeah, that's about it for the ultrasonic sensor. You can use 2 different ones. Actually, that's maybe another good point. If you use 2 of them, don't use them at the same time because one might not know which echo it's getting, especially if they're facing the same direction. Facing in opposite directions, not so bad. That is also a concern in FRC if you're using ultrasonic sensors. The more expensive ones, like the ones that come in the kit of parts that are about $40, they're much more tolerant to other sensors. These ones here are like a few dollars and they are not. You can easily fool them by putting another sensor in the area. And maybe if we ever do get to playing this game one-on-one, one versus one, make sure you're not pointing your ultrasonic sensor at somebody else's ultrasonic sensor because that'll definitely confuse it also. So look up ultrasonic sensors online if you want to know all the kind of pros and cons. They're cheap, but they do have some limitations. Thanks for listening.